Hello. Uh, this is today we want to talk about damped harmonic oscillator. Oops, I need a pen to write something down. So we want to talk about damped harmonic oscillator. I'll define the term damped very soon. For reference, today this is for physics 301 in SIUC. And today the date is at least the date of the computer is March 23rd, but it's actually a late night of March 22nd. That's just for reference. Let me erase that part so that it's cleaner. And let's get back to damped harmonic oscillator. Let me draw one for you like we did last time. That's a wall on which I want to attach a spring. So that's my floor. And let me attach a spring to the wall, stretch it, and connect it to a mass M. The material characteristic of the spring is described by what is called a spring constant. The mass M comes into picture, and we also want to have a frictional force, not the usual frictional force due to the floor, which is given by the Coulomb's law of friction. No, that's not what we want to have. We would like to have a velocity dependent friction, something like what we have in the case of when you dive out uh, in a skydiving scenario. There the friction is dependent on the velocity, or what is experienced by a car when it's going through air in a very fast manner. So that's those are situations where an object is flowing through a fluid. In those cases, the frictional force is usually proportional to velocity, unlike the friction on a floor is dependent on the normal force. So we want to talk about scenario where there is a frictional force due to a fluid, and that's what happens. What are the scenarios where we do talk about this? The best example is a shock absorber in a car, right? So this is a model for a shock absorber inside a car, in a car, right? Or often we have doors that do not bang on itself when you just leave the door. There are doors that smoothly close, and they usually have a, a similar a damped oscillator inside, if you want. And we'll talk about what is how do you design a door, and how do you design a shock absorber? What are the characteristics that differentiate the two? So we want to talk about the equation that governs this damped harmonic oscillator. Damped means there is friction. So let me introduce friction there. So there is a force, restoring force, which is Kx. Remember, there is a equilibrium point x equal to 0, and this is your point x. The stretch in the spring is x, and the frictional force, let's say, is proportional to velocity, and we also say that this is equal to b times the velocity, right? In terms of the velocity, v is velocity. Okay, so using Newton's law, we have mass times acceleration is equal to having two forces this time. Last time we had just the oscillator forces is minus kx, and friction is also in the opposite direction, so that's minus times b. So b is that's a coefficient of friction, right? So let me describe, so b times v. So m is the mass, k is the spring constant, and b is the coefficient of friction. I think there's only single F, right? Yes. Okay, that's good. I can immediately write this as a differential equation. So this is mass times, or first let me rewrite this onto the right, and then I replace the acceleration with second derivative of position plus b times the velocity, which is the first derivative with respect to position, plus k times x is equal to 0. All right. Clearly, it is clear that if b were equal to 0, uh, b equal to 0 leads to uh, uh, just a harmonic oscillator, no damping idea at all, right? No damping. And if b is not equal to 0, we call it a damped harmonic oscillator. So that means there's friction. Right, that's a idea. Like earlier, we divide out by mass m, and we get our equation as d square x over dt square plus b over m, which I will define it to be 2 times gamma times dx by dt. So what is 2 times gamma is equal to b over m. That's my definition. And there is k over m in the next term when I divide out by mass m. Now that I define to be the characteristic frequency x of the harmonic oscillator. Square is equal to k over m. That's our primary differential equation. How do I figure out what's the solution for this differential equation? You go by one of the methods to find the solution is that you use an ansatz, you guess the solution to be, okay, it must be of the form exponential because this is a linear second order differential equation in those scenarios. So you guess, right? Say that, oh, it must be of the form, so x of t must be exponential of some alpha times t. Notice you're not really found the solution until you find alpha, you're not determined the solution. So this is you're just claiming that, oh, it must be of the form exponential. And that's because it's a linear second order differential equation. That's a guess, so you have to put it back in there and you say what is your alpha. So where alpha is to be determined, right? So alpha to be determined. So you substitute it back and you realize that the first derivative dx by dt brings down an alpha, and the second derivative brings down another alpha again, right? So exponential derivative of an exponential is just the argument, whatever is in front of a t, you bring that down. So it's alpha square times e raised to alpha t, which leads to say that our equation, then the differential equation, seems to be alpha square e raised to alpha t plus alpha times e raised to alpha t plus, sorry, not alpha times, so there's a 2 gamma also there, right? So let me erase this a little, make some room for 2 times gamma. So I have 2 times gamma times alpha e raised to alpha t, correct? That's my dx by dt plus the characteristic frequency omega naught square times e raised to alpha t. And this whole combination has to be equal to 0 because the differential equation has to be satisfied. And one immediately sees that exponential of alpha t comes out, and we have the equation alpha square plus 2 times gamma times alpha plus omega naught square is equal to 0. Remember, our goal is to find alpha that satisfies this equation, and we have an equation in alpha times, or there is a quadratic term in alpha, and then that multiplies into exponential of alpha t to give you 0. Notice, since exponential function in general for an arbitrary time is not equal to 0, is not equal to 0, at least not for all times. Remember, alpha could be complex, so in general there are times at which that can go to 0 because this leads to could lead to oscillatory solutions, but it's not always equal to 0, and but we need this equation to be 0 for all times. That seems to suggest that alpha, so since that's not equal to 0, that implies that alpha square times 2 times gamma times alpha plus omega naught square has to be equal to 0. Right? That's quadratic equation should be 0 because for every time t, the differential equation is satisfied. And that quadratic equation has 2 solutions, and alpha is equal to minus 2 gamma divided by 2, so the solution is minus gamma plus or minus, and b square minus 4ac divided by 2b square is a 4, and the denominator 2 cancels out with it, so it's gamma square minus 4 omega naught square, so it's omega naught square. Since we would like to compare it with the harmonic oscillator, which has omega naught in it, so let's put that, this can also be written, there's nothing wrong in writing it in this form, but we will find it convenient to pull out a negative sign, write it as a imaginary quantity, and this is omega naught square gamma square. Right. So that's 2 solutions, and remember, we have, if you have a second order differential equation, you do need to have two independent solutions, and it's e raised to alpha t and e raised to alpha 2t. So the independent solutions are, or the linear combination of the independent solution which forms the solution to our differential equation will be a times, let me write a prime so that I can, when I write down the final form, I'll write my a's. So this is exponential of alpha t, but alpha, the first solution. So that's minus gamma plus I omega naught square minus whole thing multiplied by t. So that's e raised to alpha t, right? That's your first solution. But since there are two solutions, the plus or minus, right? So that's a linear combination of the two solutions is the total solution, right? And a prime and b prime acts as the integration constants. So it's minus gamma minus I t. That's clearly your solution. And in fact, like earlier, we can write it as exponentials, or we could also write it as in terms of cosine and sines, right? So let's express that, and or before that, I can bring out an exponential of gamma t. That's your damping. Anywhere that is gamma showing up, that's a characteristic of damping in this case. Right? So this is a prime times exponential of I omega naught square minus gamma square times t plus b prime times exponential of minus I square times square t. I can write the exponential in terms of cosine and sine. Recall cosine of omega or cosine of theta. Let me undo so that I don't have cosine of theta is e raised to I theta plus e raised to minus I theta over 2, and sine of theta is exponential of I theta minus exponential of minus I theta divided by 2 times I in this case. And using that, I can actually replace the exponential in terms of cosine and sines. So remember, so this implies like I can add these two quantities out. So I can write exponential of I theta is equal to cosine theta plus I sine theta, and exponential of minus I theta is cosine of theta minus I sine theta, right? So in principle, I can, or these exponentials can be replaced with cosine and sine, and that lets me, it allows me to write my solution as exponential of gamma t times so that will be cosine and cosine in there. So this will be a prime plus b prime times cosine of omega naught square minus gamma square t. And I also have an I in there. There's a minus sign, so this is plus I times a prime minus b prime, correct? And we have this time the second term is given in terms of sine. Of course, I don't have to call this a prime and b prime. I can give it some new variables. So just erasing this part so that I make some room for myself. And I can write the solution as, which is what we will use. So that's gamma, and you have a times cosine of omega naught square times gamma square plus b times sine of square minus gamma square times t, where we used the notation a is equal to a prime plus b prime, and b is equal to I times a prime minus b prime. So it doesn't matter because a and b are two different integral constant. We have to give some initial conditions to the problem. So then we can specify our a and b. So initial conditions, only then this differential equation really gives you unique solutions. So the initial conditions are going to be x of 0. Let's keep it very general. It's going to be x naught, right? And v0 is velocity at time t equal to 0 is v naught. And that's what we would like to find a very generic solution for this scenario. Let me go to the next page, and before I proceed, I should point out a few things here. Notice that the frequency with which the mass oscillates, right? So the frequency of oscillation is omega naught square minus gamma square, which is less than omega naught. So if you have damping, the frequency oscillation is slightly smaller. Like if it oscillates at all, there is a situation where it might not oscillate. So that's what will be called overdamped oscillations. In that case, it doesn't oscillate at all. But if there are oscillations, they are going to be, the frequency of this oscillation will be smaller than the case of no damping. And further, this exponential term actually kills the solution as we go, and we'll see later how we can plot these scenarios. But let's characterize this solution. Notice what are the parameters in the problem. It seems like so the parameters seems to be omega naught, right? That describes how the tendency of restoration, right? That's the oscillatory tendency. So this is oscillatory tendency. Gamma is damping. This describes how much damping is there. And it's a ratio that comes into picture. And we also have x naught is your initial, x naught, and v naught is your initial conditions, right? We can immediately, and let me write the solutions here, and let me put it, since I cannot refer back right here. So this is exponential of minus t, and I have a times cosine of omega naught square plus b times sine of. Okay. We need to find the a and b's in terms of x naught and v naught. For that, I need the velocity itself, and for that, I need to write down the first derivative, right? So v of t, which is the first derivative of position with respect to time, that's equal to, there are times showing in the square bracket and outside. So if I were to take the derivative with respect to the exponential, it brings down a gamma, but then it gives me back the exponential, and that's nothing but x itself. So it is minus gamma times x of t as a whole. The whole solution with the minus gamma is what you get when you differentiate the time and the exponential, but then time also appears in the sine and cosine. So there's a distributive property of differentiation, and it gives me exponential of minus gamma t. And when I differentiate the cosine, it becomes sine, but both terms will give you the coefficient. So you can pull it out right away here. And what I do get is omega naught square minus gamma square will come out from both terms. So I'm sort of jumping a step here, and cosine becomes a sine. So this is a minus a sine of omega naught square minus gamma square t, and the second term becomes a cosine. That's your second term in there. Our initial conditions say that x of 0 at time t equal to 0 is x naught. So use the first as the solution itself, x of t there, and we immediately get x naught is equal to, at t equal to 0, the exponential term doesn't survive, sine term doesn't survive, so it's just cosine gives you 1, so it's just a. Right? So we immediately know a now. And once we have a, let's go to the second equation. Velocity at time t equal to 0 is v naught. And that gives me, from the second equation, v naught is equal to x of t. I did say or x at time t equal to 0 is actually x naught, or it is a, which is actually x naught. So it is minus gamma times x naught plus exponential this time goes away, and we have omega naught square minus gamma square and again this time the sine term doesn't contribute, the which is the coefficient of a, but it is b that contributes, so it is b here. So these together imply that a is equal to x naught and b is v naught plus, so damping coefficient gamma times x naught divided by omega naught square minus gamma square, which then substituted into the first lines of solution and the expressed in the first line gives you the solution in terms of the initial condition. So this is the solution, so the complete solution. Right, so let me write solution here. Right, so x of t is equal to exponential of minus gamma of t times a, which is x naught, then we have cosine of minus omega naught ski. I said that the frequency with which it oscillates is slightly less. That's the square root of omega naught square minus gamma square. And B now is naught plus times sine omega naught square times t. That's your total solution. In terms of the 4 parameters that we described up there, and which 2 of which are initial conditions, and it seems like there are 2 parameters, omega naught and gamma, that describes different scenarios, but we will see that that's not the case. But before we proceed on to the analysis of that, let's describe some scenarios. Let's take omega naught to be the reference because that's the simple harmonics solution. Correct. So first scenario is, of course, when the damping coefficients gamma is equal to 0. So no damping. That's called a harmonic oscillator, right? That's our old harmonic oscillator. Right. And in that case, of course, the solution simplifies to x naught cosine of omega naught t plus v naught over omega naught times sine of omega naught t. Right. This is what we had covered in an earlier lecture, just that I recorded right before this. Next solution is, since we have the square root form, there is a scenario where there is gamma naught, but it is actually small. Right? Gamma naught is small compared to omega naught. Right? So there is this frequency with which the mass is oscillating, and in the same units, the coefficient gamma is not significant compared to the characteristic frequency of oscillation of the harmonic oscillator. This we will say is a damped harmonic oscillator, or we will give it the name underdamped harmonic oscillator. And this case is what the solution that we expressed is most suitable for this case. Once we realize that the gamma less than omega naught is going to be defined this way, it is good to ask, what is gamma equal to omega naught? That's a very special scenario where the parameters in the problem, the spring constant and the frequency, just has to balance each other, and that will be called critically damped harmonic oscillator. In fact, there is no point in talking about it as an oscillator because it never really completes one or one period. It takes infinite time to actually complete the period. That is the case because it's the frequency omega in this case. So omega is equal to omega naught minus gamma square is equal to 0, which implies the time period t is infinity. Right? That means the oscillator never comes back. It keeps trying to finish its first oscillation. It takes infinite time to just finish its first oscillation. And we'll talk about that. And then we, of course, have the scenario when omega naught is less than, so that is when the damping term dominates over the oscillatory term, and this will be called overdamped. Overdamped solution. And it is the overdamped solution that is used in a car, like the shock absorber in cars, shock absorbers. And a critically damped oscillator is what is used in a door automatic doors, right? That doesn't bang on itself when you let it go. And why do we use that? The characteristic of this critically damped oscillator is that it does die down, but that's the shortest way it can die down. An overdamped oscillator will take more time than the time t equal to infinity, in the sense that for the same amount of stretch, it will take a longer time. They all have infinite time periods. And of course, one can talk if one wants to, which is so if you want the damping term really dominates when this is infinity, which is equivalent to saying that omega naught very much less than the damping coefficient. Let's talk a little bit about the character of the solutions for this problems. Right. Of course, if I have, that's my time t, and this could be my solution x of t, and if this is the case when gamma is equal to 0, right? That's a simple harmonic oscillator. When so this is your t, and we can talk about the scenario where is less than omega naught. That means there is damping, but that's not significant enough. So that's characterized by, let's say, we do, so there's, for reference, we have this exponential of, this curve is exponential of minus gamma t, right? So it's so t, and you can put the same term here also. This is just for reference. This really is not the crucial point. It could start from 0 or somewhere else in general. We have a solution like this, and notice that could, so this envelope exponential of gamma t acts like an envelope, but this is not a perfect envelope in the sense that there is a small region where the actual solution could be greater than the envelope exponential of minus gamma t. So with that care in mind, this is what a damped harmonic oscillator looks like. That's very intuitive. uh, it exponentially dies down, the amplitude exponentially dies down, and its oscillation frequency, remember, is so this is your time period, right? So that's your time period, right? Here, the time period between two peaks, if you want, t, so this is t naught, this is a simple harmonic oscillator. In that case, that is less, so this t will be greater than t naught. Right, that's all. And so that's your underdamped solution. Next, we have, if we keep increasing our gamma, we will have a scenario where this is when the damping coefficient becomes exactly omega naught. And that's when, so notice this t gets larger and larger compared to t naught. And eventually, when the damping coefficient is exactly equal to omega naught, so this is your exponential of gamma t, and that's your gamma t. So this never goes down. And the solution here, remember, x of t would be equal to, I have to substitute omega naught equal to gamma naught in the earlier page. So let me refer to that. So if you were to substitute this to be equal to 0, cosine of 0 is 1. Sine of 0 seems to be equal to 0, but then I can always divide by time t and multiply by time t there. And in that case, when you take it to 0, that gives you 1 in there. And the solution is then, so let me go back. So solution comes out to be x naught times plus, actually. So this is v naught plus the frequency or a damping coefficient times x naught and multiplied by time t, and the whole thing multiplied by exponential of minus 2. Notice for some time, for when t is equal to 0, this has to go down, and this is that small increase that you see here. Right? So in the early stages, it tries to grow, and that's because of the linear term in the square brackets. And later on, the exponential for large t's, the exponential dominates, and it is an exponential decay, right? And in this case, the time period t doesn't come back, so that tends to infinity. And if you further increase your damping coefficient, if you go greater than omega naught, then you still have this decay, but now you could have much more. It will take a lot more longer time to decay, right? So this is a relatively larger time period, right? So this is relatively larger t, but still you have t time period t is still infinity, but it is relatively larger than the time period for the for for critically damped case. So this is critically damped. So either way, either it is critically damped or over damped. Both are good when it comes to damping. But for certain problems, for example, if you have air conditioning and you're using a door that closes onto itself, you don't want to take it forever to come back. So you want to get it as soon as possible. So you would use a critically damped uh, solution for that purpose. It seems like t takes t equal to infinity, but remember, most of the stretch of this exponential term, which is usually about 67%, is covered in a small amount of time. It's like the way we charge a capacitor. We talk about time constant. So t equal to infinity is just the scale of the problem, but typically we talk in terms of time constant. So that's a very general solution for damped harmonic uh, oscillator. And it's also good to go over each case separately. For example, it is good to ask, so some of the extensions or homework problems, what we will be covering is what happens when omega naught is equal to 0? What is that solution correspond to? That seems to suggest that our equation is simply mass times acceleration plus b times velocity is equal to 0. Right? We can always get the solution for this case from our general solution. But it's nice to see how this works out from the early stages itself. But we'll cover this somewhere else. For now, I think it's long enough a video, and I'll try to stop this at this point. Thank you, and talk to you in the next video. So we'll stop the recording here and stop.